We know that there are various instruments for length measurement, such as meter rule, measuring tape, vernier calipers, and micrometer screw gauge. In previous sessions, we looked at how to find the length using meter rule and measuring tape. However, there are certain lengths that are just too small to measure with these instruments. Examples of these include width of a coin, diameter of a ball bearing, width of a book cover, and so on. We might be able to measure these lengths using tape and ruler, but the uncertainty in the readings will be high, leading to inaccuracy. For these smaller lengths, we either use vernier calipers or micrometer screw gauge, simply because of their greater precision at measuring these lengths. Vernier caliper may be manual or digital. The key difference between the two is the LCD display. Apart from this, the structure is largely similar in both cases. In manual instrument, the reading on both scale is noted and is added to give a final instrument reading. Meanwhile, in digital instrument, the final reading is automatically displayed on the LCD display. Vernier caliper is used to measure lengths that might be difficult to determine with meter rule or measuring tape. They can measure lengths typically up to 15 centimeters. They have a metallic frame and can measure regular shaped objects such as ball bearings, cylinders, and cuboid that might be difficult to predict accurately with the meter rule. The word caliper refers to two sets of jaws that can be used to measure the external diameter or dimensions of an object. The main scale is a long metallic scale with the jaw or caliper attached to the front end. The upper side is marked in inches, while the lower end is marked either with centimeters or millimeters. It is also referred to as the fixed scale. The vernier scale is a metallic piece with 10-digit markings on it. The vernier scale slides on top of the main scale. It is also referred to as the moving scale. The front end of the scale is also connected to a jaw or caliper. The caliper attached to the main scale is fixed, while the caliper attached to the vernier scale is free to move. Together, these jaws form the external calipers or jaws of the instrument and is used for measuring the external diameter or lengths of different objects. At the top, there are two calipers, one attached to the main scale and one attached to the vernier scale. They are known as internal or upper jaws because they help to determine the internal diameter or dimensions of an object. At the end, there is a small retractable metallic stem. This stem is used to measure the depth or height of a small hollow object. Just to recap the structure of a typical vernier caliper discussed previously. The upper jaws used for measuring the internal diameter of an object, the lower jaws used for measuring the external diameter of an object, the main scale which is fixed and has markings on it in either centimeters or millimeters. We then have the vernier scale which is free to move on top of the fixed scale. It has only 10 digits starting with 0 and ending with 10. On top of the vernier scale there is a screw clamp which is used to lock the vernier scale down to prevent it from sliding while taking readings. There is also a retractable metallic stem for measuring the depth of a hollow object. We know that vernier calipers has two scales, main scale and vernier scale. The total device reading, therefore, should be the sum of individual readings of both scales. Before we move further, it is important to discuss least count. Least count is the minimum value of length that can be measured by the device. In case of vernier caliper, it is 0.1 millimeters or 0.01 centimeters. It is crucial that you remember both values, and in later sections we will discuss memory aids to help you remember least count of all instruments. A reminder, vernier caliper has only 10 digits. Even if the digits are not marked on the scale, you need to remember intuitively that it starts from 0 and ends on 10. Drawing both the vernier and main scale completely is cumbersome, so the scales are represented as if two rulers are joined side by side. We have a vernier caliper below, and we use it to measure the diameter of a ball bearing. When we place the ball bearing between the jaws, the vernier scale slides to give a particular value. If we look closely, We can see the markings of the main scale. Let's represent them by red lines. We can also see the 10 digits of vernier scale. Let's mark them with blue lines. When the ball bearing was placed between the jaws, the vernier scale moved and these lines also shifted towards the right. MSD corresponds to main scale digits and VSD corresponds to vernier scale digits. These diagrams show multiple cases of vernier calipers. In each case, the smaller ones represent the vernier scale. This scale has 10 digits starting from 0 and ending on 10. Even if the digits are not marked, they are shown by the red lines. The other larger scale represents the main scale. The markings on this scale can be in millimeters or centimeters. They are marked by the blue line. Total instrument reading is equal to main scale reading plus vernier scale reading. In this section, we will discuss the main scale reading. Main scale reading is that value on the main scale or fixed scale that appears immediately before the 0-digit mark of the vernier scale. In the case below, we have scales representing vernier caliper. The shorter one represents the vernier scale, while the longer one represents the main scale. First, we locate the 0-digit mark of the vernier scale. This is marked by the red arrow. Main scale reading is that value on fixed scale immediately prior to this digit. So we draw a line on the fixed scale value immediately before the 0-digit mark. This is represented by the green line. We now need to know the value of this digit on the main scale. This value lies between 30 and 35 millimeters, and the distance between those values are 5 digits. So each digit corresponds to an increment of 1 millimeter. So value after 30 millimeters is 31 millimeters, 32 millimeters, and then 33 millimeters. The value 33 millimeters corresponds to our green line marking. Therefore, the main scale reading is 33 millimeters. Let's repeat the entire process on another example. Again, we first locate the 0-digit mark on the vernier scale. This is marked by the red arrow. Main scale reading is the value on fixed scale immediately prior to this digit. So we draw a line on the fixed scale value immediately before the 0-digit mark. This is represented by the green line. We now need to know the value of this digit on the main scale. This value lies between 6 and 7 centimeters, and between those values are 10 digits. So each digit corresponds to an increment of 0.1 centimeters or 1 millimeter. So value after 6 centimeters is 6.1 centimeters, 6.2 centimeters, 6.3 centimeters, 6.4 centimeters, and then 6.5 centimeters. The value 6.5 centimeter corresponds to our green line marking. Therefore, the main scale reading is 6.5 centimeters. In the last example, we will again repeat the process. First, we locate the 0-digit mark on the vernier scale. This is represented by a red arrow. Main scale reading is the value on fixed scale immediately prior to this digit. So we draw a line on the fixed scale value immediately before the 0-digit mark. This is represented by the green line. We now need to know the value of this digit on the main scale. This value lies between 2 and 3 centimeters, and between those values are 10 digits. Each digit corresponds to an increment of 0.1 centimeters or 1 millimeter. So value after 2 centimeters is 2.1 centimeters, 2.2 centimeters, and then 2.3 centimeters. The value 2.3 centimeters corresponds to our green line marking. Therefore, the main scale reading is 2.3 centimeters. The formula for calculating vernier scale reading is coinciding digit multiplied by the least count. Least count is the minimum value of length that can be determined by the instrument. In case of vernier calipers, it is 0.01 centimeters or 0.1 millimeters. So the value is dependent on the scale marked on the main scale. If it is in centimeters, then use 0.01. However, if the scale mark is in millimeters, then use 0.1. In later sections, we will discuss shortcuts to remember the value of least count for all instruments mentioned in your syllabus. The coinciding digit is that digit on the vernier scale that clearly overlaps with any main scale reading. We know that the digit overlaps with main scale if together they form a straight line. Note: in any measurement, there will always be one coinciding digit and not more than one. In other words, there will always be one unique coinciding digit during measurement. Let's implement this knowledge to an exam level question. We first look at all the digits of the vernier scale to check which digit matches or overlaps with the main scale reading. It seems the fifth digit overlaps completely, and we will check this by drawing a line across them. This line is the black dotted line. So the coinciding digit is fifth digit. We now need to look at the scale to determine the value of least count to be used. In this case, the scale mentioned on main scale is in millimeters. Therefore, the value of least count is 0.1. The vernier scale reading is 5 multiplied by 0.1 equals to 0.5 millimeters. In the next question, we will simply repeat the entire process. We first look at all the digits of the vernier scale to check which digit matches or overlaps the main scale reading. It seems the fifth digit overlaps completely, and we will check this by drawing a line across them. This line is the black dotted line, so the coinciding digit is the fifth digit. We now need to look at the scale to determine the value of least count to be used. In this case, the scale mentioned on main scale is in centimeters. Therefore, the value of least count is 0.01. Vernier scale reading is 5 multiplied by 0.01 equals to 0.05 centimeters. Another question to ensure the entire process is clear. We first look at all the digits of the vernier scale to check which digit matches or overlaps the main scale reading. It seems the third digit overlaps completely, and we will check this by drawing a line across them. This line is the black dotted line, so the coinciding digit is third digit. We now need to look at the scale to determine the value of least count to be used. In this case, the scale is not mentioned. However, we can see the value lies between 2 and 3 centimeters, and there are 10 digits between them. This scale cannot be in millimeters as it will give an instrument reading much shorter or precise than our least count of 0.1 millimeters. Therefore, the scale is in centimeters, and the value of least count is 0.01. Vernier scale reading is 3 multiplied by 0.01 equals to 0.03 centimeters. We have calculated the main scale reading and vernier scale reading individually. In order to determine the total device reading, we simply add the two together. So total device reading is the sum of main scale plus vernier scale readings. In the first case, our main scale reading was 33 millimeters and vernier scale reading was 0.5 millimeters. Therefore, the total device reading will be 33 plus 0.5 equals to 33.5 millimeters. In the second case, our main scale reading was 6.5 centimeters and vernier scale reading was 0.05 centimeters. Therefore, the total device reading will be 6.5 plus 0.05 equals to 6.55 centimeters. In the third case, our main scale reading was 2.3 centimeters and vernier scale reading was 0.03 centimeters. Therefore, the total device reading will be 2.3 plus 0.03 equals to 2.33 centimeters. Below we have a vernier caliper. As nothing is between the jaws, we would expect a 0 millimeter reading. This happens when the 0 digit of the vernier scale matches the 0 digit of the main scale. In this case, red lines represent the main scale, while the blue lines represent the vernier scale. As the zero digit of both lines meet, we can say that the device reading is 0 millimeter. Ideally, this should be the case always. However, vernier calipers are physical instruments and are vulnerable to degradation caused by wear and tear through normal use or mechanical faults developed through careless handling. So there are instances where the zero digit of the vernier scale does not match the zero digit on the main scale. It is either towards the left or towards the right of the zero on main scale. The device is giving us a certain reading, even though it should not, especially when there is nothing between the calipers. In this case, the fifth digit on vernier scale overlaps with the main scale, so the device is recording 0.5 millimeters when it should read 0 millimeters. This discrepancy is known as zero error. Zero error occurs when the zero digit on the vernier scale does not match the zero digit on the main scale, especially when no length is being measured. In other words, the device is faulty in length measurement. In this case, the vernier scale is to the right of the zero mark on the main scale. It gives an extra value of plus 0.5 millimeters. The zero error in this case is positive. In other words, the device will measure an extra zero point 0.5 millimeters for any value of length being measured. Such an error can be corrected by subtraction of excess amount from device reading. This correction is known as negative zero correction because the amount is subtracted from the device reading. On the flip side, the vernier scale could be to the left of the zero mark on the main scale. We can see the sixth digit of the vernier scale matches the main scale, so the device reading is 0.6 millimeter. If the device was normal and not faulty, then the zero digit would have matched the zero digit on the main scale. In this case, for any value of length, the device will be short by 0.6 millimeters. Such an error can be corrected by addition of excess amount to the device reading. This correction is known as positive zero correction because the amount is added to the device reading. So before taking any reading, all vernier calipers must be checked for zero error. If it is found that the zero error exists, we must then adjust the device reading for positive or negative zero error.